Welcome to the Probability Podcast. Discussions on emerging and converging technologies, problems that are being solved, and the probability of positive and negative outcomes that we might expect. Now, please welcome your hosts, Jason, the generator Spracklin, and Patrick, the discriminator Lozon.
Hey everyone, the topic for this week's podcast is the fascinating world of computer chips, those tiny powerhouses that drive our modern world. From quantum leaps in processing power to groundbreaking advancements in materials and design, the world of chip technology is evolving at an incredible pace. Today we'll explore the latest advancements in quantum computing, including Microsoft's Majorana processor with its topological qubits, and Google's Willow processor, which is tackling error correction in a revolutionary way. We'll also examine the ongoing developments in silicon-based chips, including new materials like graphene and design innovations like gate-all-around transistors, plus the rise of lightronic chips, which may be 1,000 times faster than silicon. Finally, we'll touch on the global landscape of chip manufacturing, looking at the key players and the intricate supply chains that make it all possible. So Patrick, are you ready to buckle up and take a quantum leap?
Absolutely. Yeah. So let's talk a little bit about this. First off, there's anyons or anyons, however you want to say that. This is we'll call it a recent. It was originally the idea of an anion was kind of brought up, I guess, in the early 70s, and then it was confirmed. Basically 20 years later. So this is fairly recent discovery, right? That there's this, this group of, we'll call them particles, but they're not really.
We'll say it was a quasi-particle. So what's a quasi-particle?
It doesn't, that it's actually, they're not even, they're kind of groups of particles too.
Sounds like it was my attendance record in high school. I had quasi attendance in high school.
It was quasi, yeah. In any case, like this whole thing about anyons and how they exist and do they truly exist and how they really behave. Well, the idea behind, of course, is what we're searching for with quantum computers is the ability to exhibit quantum behavior with certain types of materials, right? So they take certain metals, they press them down into with a middle layer where it's so small that they can work in they can only move in a two-dimensional space, and that forces them to behave like what they call an anion when they put it under a lot of magnetic field strength, right? So once you exhibit that, or once they are put into this very strong magnetic field in a almost absolute zero condition, they jump certain quantum levels of energy. You can only move in certain directions. So that all being said, right, this is important because what Microsoft is claiming is with this type of chip, they can scale up the qubit range into millions with this architecture. Let's call this topological architecture.
So right now it's right?
Yeah. So right now we're like 256 or 512, whatever. We're not we're maybe in the 1,000 range, right? On the different types of quantum chips. And now, right, through this anion approach, they say they can, kind of mimic the behavior of, quantum. We'll say that, the spin behavior, we can just reverse. When you subject we'll call it a molecule to a microwave burst, you can actually, when it's that cold, right, near absolute zero, the orbiting electron can actually lock itself into a certain position on the spin range, right? So it can maybe spin up, spin down, and the idea is you can adjust it. You can apply a certain, so much microwave energy at a certain range or certain hertz, and it will slowly adjust right through the range, like 360 degrees, right? So when you go to measure something, you actually lock it. Okay, this is the strange, wonderful world of quantum. So actually, when you go to measure, it says, okay, I'm up or I'm down. I'm not really in between, right? The old Schrodinger's cat, dilemma, right? What I'm talking about is anyons. They have a little bit different behavior. They're doing what they call braiding. They switch positions. I don't want to get into physics with it, but let's just say it's sufficiently weird. Okay. It is very strange. And when you start talking to physicists about this, they start talking about statistics and, some strange, formulas and stuff, and it doesn't make a lot of sense.
Yeah, well, if anybody's interested in sort of, what quantum computing is and what qubits are, I mean, we went pretty in depth with that in the Spooky Action at a Distance, which was a podcast we did, last season. And the reason why
It
we're
still
sort
haunts
of,
us.
yeah, it's still pretty spooky.
It's still pretty spooky.
The reason why we revisited now is because of all these sort of breakthroughs. It wasn't that long ago we talked about that, and since then, like you said, Microsoft with this Majorana chip has made the breakthrough that people thought was maybe further away. Google made a breakthrough with their chip, so it seems like we're now all of a sudden quickly accelerating towards this becoming more of a reality, right? Because before it was not overly feasible, maybe for consumer applications or even just it wasn't. It was all sort of theoretical to a point, right? And we're having trouble controlling it. We're having trouble with, I think, noise levels, which is what I think they've sort of solved a bit with the Microsoft version, which is apparently a pretty big deal, as well as in Google's version, they've made a big leap in terms of error correcting, because we're dealing with a whole different sort of level of complexity when we're dealing with things at the atomic sort of level. But it's sort of, in terms of computing power, I guess it's kind of infinitely scalable. Is
That's
sort
right.
of the idea,
It's
right?
highly scalable, and the idea too. It's also apparently, when within this atomic realm, if you set something and then it loses its state, that's called, inability to maintain coherence, right? So the idea is that you want a long duration memory, so to speak, of a setting. So this coherence setting or behavior, I mean, is it's a major issue, and that's one of the reasons why they have to, they build these very expensive, containers around these devices, and they have them in near absolute zero conditions. I mean, it's pristine to be pristine, that's a very expensive machine. It's very expensive to build, very expensive to run, right? And the more they can, we're going to see more of this. We're going to see more developments and exotic types of alloys and materials as they're trying to make these, these quantum computers less expensive to operate and more reliable, and they can scale up more. So this is just one example of a fairly significant advancement at the very beginning stages, right? So we're going to see more and more of this as time goes on. Can we eventually build a quantum computer that runs at room temperature, right?
Mm-hmm.
Right now, not yet, right? So it's all very interesting, but trying to understand some of the mechanisms behind the behavior and how they're utilizing it, it's a little confusing. But that all being said, we can also talk about the Google's Willow quantum processor, and it's made some very impressive calculations. It's really moved ahead the quantum computer realm, I will say um, for instance, with IBM, they've opened up the ability for the rest of the world, to actually utilize that quantum computer calculations and things like that so as a service, right? So that's where we're going with a lot of this technology is, to expose it for, researchers and scientists and technophobes to actually, perform a number of different types of experiments and learn from these devices. So one interesting thing is that as we're moving forward into, we'll say, mechanizing quantum physics, okay, we're learning a little more that there are things that are occurring at the quantum level that we never really understood or never expected. And this is a whole new realm as well. We're learning, about quantum behavior because we're actually trying to put it through its paces by our means of turning this into a reliable technology. And we're finding out some of our theories, aren't 100%. We still don't have a fermion. we don't have a firm understanding.
We have a
yet.
quasi understanding of what's
Of,
going
of,
on.
yeah.
It's interesting though, when you're trying to create a chip using this, quantum technology, you're inevitably, creating an understanding of it, but you're also then able to use it to manipulate, things in the real world, right? So, for example, they were talking about they can use quantum mechanics to mathematically map how nature behaves with incredible precision, from chemical reactions to molecular interactions and enzyme energies. So, for example, they could help solve difficult chemistry questions of why materials corrode or crack. And this could lead to being able to create self-healing materials, which used to be only the thing of Marvel movies, right? And now,
Yeah.
with sort of that type of thing is right around the corner, which is, pretty impressive. You think about like an airplane that starts to crack or break up in midair. If it was made of self-healing materials, it would be much less risky, for example, right? And then there's so many different types of plastics. It's important for tackling carbon pollution so we can, ensure that we have a control on microplastics and that type of thing, right? So there's so many different, once we get down to that like molecular level, right? And even down to like the biological level of things, we could eradicate, global hunger by figuring out how to, increase yields of crops and all sorts of things, right? Our entire world is sort of the building blocks are at the molecular level. So now we can, with this type of quantum computing, we can manipulate it. And I guess, it could also be used for evil as well. I guess we'll eventually go there knowing how your brain works. But
Well, I'm glad you said that. I mean, the idea behind this is that there are spin-off technologies and spin-off, we'll say, understandings of how things work through employing this, right? And through we're like discovering, exploring a new solar system. It's only super, super small, right? Now, the other thing too, of course, is which you didn't mention, which is super weird, is they talk about different dimensions and they talk about time, right? And entanglement is another weird one, right? Where, you can entangle two quantum, particles or qubits, which are really entangle the two electrons, let's say. And the idea behind that is that you can take those two electrons, you can separate the electron and send it light years into space. And if you do something to electron A, the mirror, electron B, will change as well, right? The behavior will shift, right? Just as A changes, B changes. And the distance between the two doesn't seem to matter. So we are getting into the fundamental dimensional properties of space and time.
That's the spooky action at a distance
That's the
we
spooky
talked
action.
about earlier, right?
Yeah, yeah. Like they talk about this Majorana chip and how it remembers how it, like if you apply a certain energies to this chip, and it adjusts, it performs this braiding movement, which is basically a flip, and it remembers how many times it's flipped. It'll rewind itself and knows exactly where's it. How can that happen? It's not a brain cell, right? We're talking some weird stuff here, right? And you think about the dimension of time, right? Like if you're really, putting all the pieces together, it's not about memory. It's about rolling back time. Okay. I know this is like a bad science fiction movie, but the idea is that this is what we're getting into. We're getting into the murky, spooky stuff. And I think I really love about this type of technology. And all these are like millions of little mini experiments being run, right? When the idea that they run these quantum computers and they do modeling with them, and they're coming up with perfection, but they're also coming up with results which they didn't anticipate, and they can't quite explain, right? And again, I mean, they do the same thing, of course, with AI, but to me, that's discovery, that's learning, that's the mysteries of life, right?
Yeah,
And
it's entering the
that.
unknown, right?
Yeah,
Is really what it is. But then along with that, which I'm sure we'll probably get to though, is that we're kind of playing with, fire maybe in a way, in that because we're venturing into the unknown, we don't have a firm grasp on like what might happen, right? And I
Oh, now
forget
you sound like those guys with the Large Hadron Collider, and we're gonna create a black hole and suck Earth in.
yeah, wasn't that the whole thing? But wasn't there a big hydrogen collider type machine that really was at risk to causing something pretty catastrophic at some point, if I remember correctly?
Well,
Or was
that
that a
was an
movie?
underlying risk. The idea is that they would evaporate and never grow to any particular size that would make any difference. But the ideas behind this is that we don't know what we don't know,
Hmm.
right? And we are exploring, and you can never eliminate. And despite what the smartest minds in the world say, right, you can never eliminate risk if you don't know what you don't know.
So we're either going to rip a hole through the fabric of space and time, or we're going to have really cool cell phones, like really fast quantum cell phones. I mean, it's kind of worth it, right? We might
Yeah,
destroy the known universe.
and Skeletor will come out.
Yeah.
Yes.
Or
Yeah.
we'll just have, blazing fast cell phones that can, compute the entire history of Earth's knowledge in 3 seconds.
Okay, so yeah, Willow is they're still learning on that one. It's a great platform. IBM again, they got their Condor processor. IBM's breaking. I think that everybody likes to talk about Microsoft. Everybody likes to talk about Google, but IBM's they're not a slow player here. They're a leader.
Well, they were
in this
the
area.
OG, right? Like they were the ones
Yeah,
that innovated in chips and hardware
yeah,
and that type of thing for many, many years before other companies really
that's
started to
right.
get into the game.
Yeah, and they spend billions, right, a year doing R&D. So they're a major player in this. And the idea behind it, of course, is that um, you don't know how to harness these technologies until you do the R&D. You spend the time, you spend the money, and you figure out the ways, right? And you have to be creative to sort. I mean, the amount of thought to build these quantum computers mind-boggling, right? But it's also, interestingly enough, you know, it's like AI. You know, it's not a linear line, right? The curve goes up. So as we learn about these things, the curve starts banking up, and then we start applying, our theories that are proven, and then we get to a point where we can commoditize some of our technologies, and the curve goes steeper. And what's interesting about this is now we employ AI as one of our tools to augment our discovery and thought process, and the curve goes even sharper. Pretty soon we're making like exponential changes, right? And this is what I see in the future. I see very difficult problems like this accelerating to being solved, right, at an accelerated pace, right? And with that, I think we'll benefit, or we end up in a black hole.
Well, it's a toss-up, right? But I think
Yeah.
that ties into Moore's law, right? And now we're sort of like Moore's law is not necessarily based on, physics. So Moore's law was the idea that the number of transistors in a dense integrated circuit doubles every 2 years.
Doubles every 2 years. Okay.
And we've sort of, far exceeded that, right? How does Moore's law apply in this particular case then, right? Because we're about to enter a whole new realm of quantum computing and other chip technologies where things are going to grow so much more exponentially now, right? This idea of things doubling every 2 years is going to turn into doubling every 2 weeks, type
Well, that's
thing.
the thing. I mean, what was how many qubits was Willow? Was it 16 or something originally? And now we're talking with Majorana, we're talking scaling up to, at least like they're talking millions. I need to see that first. But I mean, originally, we were using like 4 or 5 qubit, like small amounts, right? With our models. So the intent here is that by scaling, right, you're going to end up being able to perform larger and larger calculations, right? Now, if you think about it, the idea of where encryption is based on like using prime numbers, multiplying them together, coming up with a key. The idea of finding those root numbers, is nearly impossible from a calculation perspective. With our existing computers, it takes too long. It's not impossible. It just takes too long. So the idea being that with this new type of computer that can do so many calculations simultaneously, we're dealing with breaking down the compute time, from 40,000 years to 4 minutes.
Right? Yeah, there's a reference to all of the computers in the world would take 11 trillion years to solve a problem that a quantum chip could solve in 3 minutes or something, right?
Yeah,
It sounds like the thing of science fiction, but that's the kind of scale we're talking about. But I think the biggest problem, one of the biggest problems in scaling was this idea of like error correction. So that was the big breakthrough from Google. So what did that really mean? Like, how were they able to figure that out when other people were not, right? Because when you can scale up this power and not, I guess the problem was that there was they were able to scale up the power, but eventually the errors would ruin the computation. You'd end up with, I guess, sort of something incorrect or garbage coming out the other end, and Google was able to solve that in particular. I think Microsoft solved the noise problem, but Google solved the error correction first.
Yeah, when you think about it, like the exact answer for that, I can't give you right now.
Oh, come on, Patrick. You're a quantum expert, right?
Yeah.
I mean,
yeah.
I'm not. My true knowledge of quantum kind of starts and ends with Ant-Man, but back to Marvel again. But
yeah. It's the idea that you have all these different qubits, and they're all simultaneously working, and one can through basically with, I would say, coherence issues, right? It would come up with noise, right? And the intent is to being able to isolate those particular calculations, throw them out, because that's noise, right? Um, and at the same time, the intent would be to reinforce, it's like a frequency sine wave, so to speak, that you uh, apply to those those group of qubits, and it basically reinforces the answers, and with that you get the final results, right, through the act of observation, which is locking the reading in. Okay, but you got to know when to throw out certain results, right, and rerun that cycle again. So,
Like playing poker, you gotta know when to
yeah,
hold them and know when to fold them, know
yeah.
when to walk away,
No, wait, wait.
know when
This is
to
this is
run.
this is experimental realm. It's they're building machines at the quantum level. It's not going to be a straightforward answers all the time. It's hard, right? And the idea being, of course, is that as they're solving these problems, they'll come up with new ones to solve. So I would say that people originally thought that a quantum computer would be 100 years away. Now it's here, right? So what happened to your 100-year estimate? That didn't work, right?
Yeah.
It's just like AGI. The AGI is going to be another 50 years. It's, people can argue it's here now. I mean, they pass the Turing test, right? So where do you draw the line, right? And say it's here, right? So,
But it's been a long process, right? One of the things when I watched the video on Microsoft's breakthrough was that they said that they've been investing in this for like decades,
they
right?
have,
So it's not
yeah,
like something that they just sort of spent a year on and they, cracked the code, right? And I think the overarching point there was that in order to have these breakthroughs, you have to kind of play the long game. You have to make that investment and you have
yeah,
to sort of play that long game over many decades sometimes to get to this point. If they hadn't started the process of trying to figure out this quantum chip 20 years ago, they wouldn't be here now, which is interesting because it sort of speaks to some of the push sometimes, in the corporate world to try and get something, built and out very fast, right? Because it's all driven by financial
quarter by
or other.
quarter thinking.
Yeah. And so instead of giving, teams the time to really dig in and really understand things and innovate and make breakthroughs, you're really just trying to like crank out product. Whereas something like this would have been impossible for them to achieve in a short period of time, right? So now I'm
Yeah,
sure even Google's been working on it for decades. So it's sort of the idea of investing in technology now and for many years with an outcome that you might not see until you're close to retirement type thing, right?
yeah, yeah. I mean, I think the anion one, this, Majorana chip here, I think it's been 4 or 5 years, right? So it's that was 4 or 5 years ago it was started. Um, Now again, that's what R&D is all about. It's about a continual investment that you pull off your bottom line, and you continue to reinvest in your company, reinvest in your people, reinvest in your ideas, right? And having companies that are brave enough to do that, not bean counting on every quarter, right? And this is where the big payoffs come, right, in the end, because once you do come up with these, I mean, everybody talked about the idea of the 3M and post-it notes and stuff like that, but let's go back in time and talk about Bell Labs way back when, right? Bell Labs are the ones that they had this R&D division, and they were putting together the whole idea behind Windows, And if you go further back, standard operating systems and the whole idea behind we're using technology today. A lot of these ideas, well, they weren't necessarily patents. Were invented in Bell Labs, right? And that's because there was, an intent, right? An intent to continue to invest. And you may actually, invent something or learn something or discover something and not be able to apply it at the time. And it takes years before, look at this idea about topological chips. I mean, that whole idea about anions and being able to build a chip like that. I mean, that was back in the 70s when they talked about that this thing could exist, right? These quasi particles and stuff like that. So things take time, right? And it takes time and investment for major, game playing shifts to really occur, right? You got to really stick to it. And so my hat's off to companies like IBM and Microsoft that are able to move this, move this technology ahead and not follow the old, well, we're not doing so well. Let's lay off a bunch of people, right? That's never going to get you where you need to go, right?
Yeah, absolutely.
Yeah.
But I guess it's still somewhat experimental. I mean, they certainly made these breakthroughs, and you're going to start to see, computers built with them. They're not going to be completely mainstream, but then there's, other advancements. So maybe we can talk about other areas in terms of, maybe we can talk about other types of chips, right? Because it's quantum chips is one way to go, obviously, and it's sort of has the most potential for this sort of astronomical computing power, but there's certainly some other breakthroughs happening as well, right?
Yes, that's right. I mean, there's electronic or photonic chips based on light, right? So the idea originally was to, especially for managing, your fiber, being able to build circuits embedded in utilizing the fiber signals, and to automatically adjust for your telecommunication control systems, and that turned into, well, we can build logic gates, we can build, the equivalent of transistors using light, right? Sensors and systems and optical gateways, and it's like, really, you can do that. And so now we've got, a number of different platforms. And it's scary how fast this is growing. This is like exploded, so to speak. Google, they have the photonic tensor core and the Terra project. I mean, they're working to help introduce, and improve not only their telecommunication side, but starting to build actual, chips and circuit boards, right? And they're, the original size of these devices, where you think about a chip, you think about it, well, that's half the size of a playing card. And these things are like, 3 or 4 times the size of that, right? But now they're continuing to shrink, right? The technology's continuing to advance. The ideas are being generated to help shrink these down to the point where they'll actually be able to compete with a silicon chip to a degree, right? And I'll say to a degree because guess what? They're not giving up on the silicon chip just yet, right?
No, for sure. Well, when you think about it, like I was watching a video the other day it was kind of like a timeline thing and showing, back in the day we had these big desktop computers and that showed things shrinking down and down and down the size of these desktop computers, and eventually the computer was basically like in the monitor, and then it shrunk down to a laptop and then to a phone, and it was trying to show that the form factor is getting smaller and smaller, the processing power is getting bigger and bigger, and we're going to see that go even further, right?
Yeah.
But when you think about it, like we lived at a time when computing was just starting. So back to the two old guys reminiscing about back in the day, right? But the idea of a supercomputer, right? Back in the day, when you saw pictures of it, was like a massive room
It
with
was.
these
Yeah.
huge computers, right?
Yeah.
And I mean, this unfathomable now, right? But now you have at CES, you had NVIDIA unveil a laptop that was as powerful as a supercomputer, right? That you could
Yeah.
carry around with you, right? And then I still remember the comparison that, if we want to go back to our episode on the landing on the moon, that they landed on the moon with less power than was in a 1980s Texas Instrument calculator,
Yeah.
right? And
Yeah.
now we're carrying around, phones that are probably as powerful as these huge supercomputers that exist in a room, and now we have these devices that we can't go anywhere without. They're in our pockets, and I mean, we're using them to send emojis to people, essentially, right?
Yeah. Well, it's
We're
important
carrying
stuff.
around supercomputers, right? So,
So we can
what are,
chat.
what are
Yeah.
we going to be doing once we get quantum chips in our phones, right? We'll
Yeah.
be able to traverse, space and time, right?
Yeah. Yeah.
It's
So we can
like,
chat.
yeah, we
Yeah.
could
Come
chat to
on.
people in other worlds or
That's
what
right.
have
Yeah.
you, right?
It'll be something
Wasn't it
silly.
Google that said when they unveiled their new quantum chip that I think I said this before, but Google said that it was so powerful that it must have borrowed power from other dimensions. Which again, it's very
Yeah.
science fiction, but now we're entering this realm where, and not just in this particular area, but across the board, where all of this technology that used to be the thing of science fiction books and television shows and movies are becoming sort of more mainstream. And it's really kind of fascinating to watch the pace of advancement in the last just 5 years has been exponential. Now something like quantum computing is just going to, further accelerate that once it becomes a little bit more mainstream, right? They made the breakthrough with these chips, but they still have to get the technology to a point where it can be used in a sort of normal fashion, right? Because I
Yeah.
think
It's
it's
not
still going to
hasn't
be
been
somewhat locked
commoditized
down.
yet,
Yeah.
for
Yeah,
sure.
exactly.
Yeah. So there's that. The other thing too is that this technology um, is also going to expand from a point of view of utilization of AI to help expand it, right? So it's going to accelerate even faster. So that all being said, let's talk about um, they, they are now building optical neural networks. Okay, so one of the things about optical systems or photonic or electronic systems is they're like 1,000 times faster than electronic systems, right? They're very very fast, and from that perspective, um, if you think about managing hardware, let's say you have a autonomous drone or autonomous jet fighter, um, it's going to be able to process and respond so fast, right? Well, of course, there won't be a pilot in these, okay, because they won't be able to stand the G's. Um, that literally nothing will be able to catch them. Nothing will be able to target and hit them. They're going to be essentially, you know, well, let's say they're going to be very dangerous machines, right? From a point of view of a war machine. Um, and that's just an analogy, right? There's other areas. I'm not talking about just war. I don't
I knew
want
you were going to go there.
to. Yeah, I know. So building optical neural networks is another integration of photonic or electronic technology. One interesting aspect too is that when you build these types of circuits and these chips, these CPUs, um, they're they're fairly immune to radiation, right? Whereas electronics, not so much, right? Um, I don't know if you ever watched that Chernobyl series. It was, they sent some, electronic machines out there, and they just basically broke down. High radiation just deteriorates, electronic systems incredibly. they had helicopter crashes. And anyway, the idea
Oh,
being
okay.
that, you know, um, these electronic systems are kind of immune to that, right? So if you're building, you're building a starship, right? This is the technology you want to use, right? I know I got my science fiction author hat on here, but I mean, really think about it. You want to look at, what's immune to radiation. That's perfect, right? Also, we got to think about the who's involved here. I can go through a quick list here of who's messing with on the R&D side. We've got MIT, we've got Stanford, we've got Caltech, we've got the European Union of Photonics, we've got Netherlands, we got UK, we got Israel, we got Japan, we got Korea, of course we got China. We got a number of different EU companies like Nokia and Ericsson. They're all have their own, photonics divisions. We've got new and interesting discoveries coming down the pipe. They've been able to integrate, and I got to say that the systems that they're building today, just like quantum computers, are integrated with, our standard, electronic silicon-based computer systems, right? So they're building hybrid systems, right? The idea is that with this technology, it opens up new doors. We don't even know what the doors are, right? So just like the quantum computer, we don't. And this is where, the idea of discovery and research and development and new and wonderful exposures will help us move forward.
Yeah, but
Right?
there's also this sort of, we talked about this many times, this kind of global technology race. And we've talked about it a lot in terms of like AI and, other technologies. But what powers all of that are the chips, right?
Yeah.
And now there's this sort of, like you just rhymed off a whole bunch of different, companies or countries that are pursuing this,
Yeah.
and we were,
I was just a subset too. I'm sure I missed a few hundred more, but yeah.
yeah, well, I mean, the interesting thing is about, how these, chips are made and distributed. So you have different countries involved in different aspects of making, I guess, like our current chips, right? I'm sure, again, quantum computing will factor into that, right? But what goes into like making a computer chip, right? You have certain chemicals, for example, right? And those, in terms of producing those chemicals that go into chips, we've got, countries like Japan and South Korea, for example, right? And then you've got the chip design process, which is most of the actual chip design happens in the US, Taiwan, South Korea, Europe, for example. So that's great. You've got the chemicals that go into the chips. You have somebody has to design them, for example, right? But then you get into like the chip making machines, and they're produced, in the US and Japan, for example. But then all these chips are fabricated, and they're largely fabricated in, Taiwan or maybe South Korea. So it's this sort of like global picture on how these chips are made. And then you had at one point during, COVID, there was this huge uptick in people wanting to buy computers, whether it was laptops or desktops or portable devices to work from home, right? Because this whole shift to working from home, and it created this global shortage of chips. And chips are used not just in computers, but in everything. In fact, I think it was, I read that car companies were having challenges because there was like one specialized chip that had to be used in one part of the car. And because they couldn't get that chip, they couldn't make cars. Because, or at least the car that they had designed, they couldn't make it because they didn't have the chip, for example, right? And it sort of speaks to this sort of geopolitical, upset that's sort of in swing now, right? Where you have companies that were trading partners no longer trading partners, and tariffs and all these wonderful things that are coming into play. And what happens when really to produce these chips, like I just went through, you have different elements that go into making the chips happening in all these different countries. And when these international trade boundaries or supply chains get disrupted, now you've got a whole different problem on your hands.
Yeah, if everybody takes the status or the position of the U.S. On their trade policies, then free trade stops, right? You cannot accomplish what we're doing today. I mean, all this integration of different companies, of different technologies, and it just stops cold, right? So right now, I mean, we might be able to build, in the U.S. and Canada, build machines that actually mass produce a chip. But we're not mass producing chips. No, there's nobody in North America that's mass producing chips. You want to know who's doing that? Talk to TSMC. They're the ones that make most of the chips,
Yeah.
right? They're out of Taiwan, right? And if they have problems, i.e., typhoons, things like that.
China takes them over.
Yeah, you remember that? Well, okay. Yeah. Who's close to the borders of China, by the way, right? Um, Taiwan and Korea.
And we've been
Yeah.
restricting chips being exported over, to China because we're trying to restrict the AI race, and yet a lot of our other chips are coming from there. So
Yeah.
I guess where I'm getting to is this geopolitical landscape, if it starts to shift and change, it could have some pretty interesting consequences on,
Yeah.
the supply of chips and what that means in terms of, how they're used and how we're able to advance as a country and this type of thing, which really speaks to this idea of trying to think about how do we guard against that for the future. If you look at what happened during COVID, where there was the big challenge was getting all the vaccines imported into the country, right? Because they were made in other countries. And of course, those countries were either wanting the vaccines for themselves or they were, working with other partners ahead of, say, Canada, for example. And I remember there was some investment made at the time to start setting up production facilities so we can make those vaccines in Canada, right? So if we ended up with another sort of a similar type virus, that we would have our own homegrown supply of vaccines. And why aren't we doing that with computer chips, right? Like, why aren't we more forward thinking about that? I think it's just sort of back to this idea of lack of foresight, right?
Yeah, exactly. I mean, the idea of having some level of autonomy um, as a country, right, on all critical um, components. So take for instance, and I'll go back to the jet, right? So if you have, if your Navy and your Air Force utilize certain chips, and those chips cannot be produced, um, within the boundaries of your border, who you at war with, right?
Yeah.
What exactly is going on here from a point of view of a conflict, and what happens when you have a problem with your electronics? You're kind of, at a standstill, right? And this is just not well thought out in a lot of cases, right? The ideas behind, oh, we can be autonomous, but you can't, right? There's just no way of doing it, right? Well, when it comes to critical capabilities, you better learn how, right? And you better get that in ahead of time, because you can't do it, at the time of, whatever that, specific issue that has occurred. You won't be able to do it in time. So that all being said, when we think about chip manufacturing, right? Just farming this all out to, a couple spots on the globe, maybe that's not the smartest thing to do.
Yeah, for sure. I
Yeah.
mean, the demand's only going to rise as well, right?
Yeah.
That if you look at now, we're getting into the realm of AI where we need, massive amounts of computing, right? That, huge server farms that are being built, which I'm sure at some point with quantum computing, maybe that'll start to course correct. But I also was looking at this idea that almost every major company now is looking at designing their own chip, right? So you
Yeah.
used to have, maybe Intel and, IBM, some other companies creating chips, but I was reading even like Meta, right, that runs Microsoft, and other companies are getting into the business of creating their own chip. In fact, that was a change that Apple made a number of years ago, was created their own quote unquote like M1 chip that's powering everything they do right now. And the reason for that, which I thought was pretty interesting, was when you buy a chip from a particular manufacturer, it's just sort of this idea that it's an all purpose chip, I guess, right? It's just made for general computing power. But when you build your own chip, you can build it very specific to the use cases that you need it for, right? And I even think I read recently that OpenAI is looking to build their own chip to power ChatGPT, for example, right? Because when it's general purpose, you can't be specific in terms of like how you want the computational power to work or how you want it applied to, again, that specific use case. So now you're going to have this idea of all these specialized chips being produced by individual companies, which in my mind can only like ramp up, the need to have even more, available, right? So you're going to have, I think if you look at it, it's sort of, what's the end game here? That in terms of, producing more and more and more of these chips. It seems to be for a long time, the game was around building innovative applications and whatnot. Now there's this sort of race for computing power amongst all these companies, right?
There's some interesting spins to this, right? You think about NVIDIA and, for instance, I mean, they're still using, and Samsung and TMSC to create their, or S, actually create their chips, right? They're claiming to be, the source company, but you go down and their reliance is on all these other subcontractors, right? So the technology to build these specialized or hybrid chips, again, you're going back to that model you talked about. They go and do the design, right? And then they farm it out. They contract it out to the lowest bidder, to create and build the chip, right? That where that gets you, of course, is commodity pricing, but where it doesn't, what it doesn't get you is that autonomous approach. Now, what's interesting here, right, is when they build these hybrid or specialized chips or compound chips, whichever way you want to call it, right, they're all going to have different designs, right? Because they're all going to have ideas on how to best implement, this AI technology, right, onto the chip, right? Now, I'm expecting, right, that they're going to use AI to design AI embedded chips, right?
Well, they already sort of have, right? Or at least they've,
Yeah.
I think we touched on that in a previous episode where that AI is designing chips to the point that that scientists that are looking at, they don't really know why it works or how it works. In other words, they're designing chips in ways that, and this is just, I think, standard type silicon chips, but the AI is designing them in strange ways that we don't understand, but yet they
Exactly.
work, and they're actually working
And they
better
work.
than the ones we're designing.
Yeah.
And then you kind of, I knew eventually we were going to get there today with
Yeah.
this combination of, computing power, especially quantum power and AI. But when you're talking about AI designing the chips, and then I sent you something the other day where it showed that they've built a robot or a humanoid that's able to build other humanoids,
Yes.
right?
Yes.
So, and now we're also, this is really getting into interesting territory,
It
right?
is.
Because we're automating factories, right? Which, theoretically could be factories making chips. So you could have AI designing the chips, manufacturing the chips, building replicas of themselves with the technology, and you're into doomsday at that point, right?
Yeah. Well, I mean, the idea too is you're creating things that you don't no longer understand how they work, right? I mean, this is danger, right? Will Robinson area here, because once you get into just let's just farm out all the thinking to our little AI brother there, and he just goes and creates these wonderful creations, and we don't know how they work. It's magic. right? Is that really where we want to be? I don't think so. I don't think so. I think we need to understand, so if these, AI come up with these wonderful designs, we better interpret them and learn how they work and understand them. And maybe, you know, we will, right? I'm hoping, right? Otherwise, we're getting into, Area 51, right? We don't know what we've got hold of, right?
Yeah.
It works, but we don't know how. So, think about all these embedded companies. Like you got Intel, AWS, Google, I don't know. Who are we anyway? Um, 10 store, they're in Toronto. Yoo-hoo! Free to go Canada. Apple, Meta. I mean, who's actually building the chips for them, though? Right? So they're going to design all these embedded chips. Who's going to build them? Mostly TLMSE, right? There's going to be Samsung in there for Huawei. And Broadcom's going to do Google. But, the idea behind that is everything goes down to this lowest contract builder, right? So
Yeah.
the idea of why are we asking about that? why? Well, it's because it's all cheaper, right? It's all about money. Well, no, it's not all about money. It's not all about money. If you're talking about you're building, we'll say state of the art R&D electronic designs that nobody's ever. This is purely exploration, and they could with a possible impact of upsetting whole economies. Right? Are you really protecting that knowledge? It was just farm it out that this one company
Yeah.
built
Well,
it. Yeah. It's all
ultimately, it's
covered
a
under
race.
the IP ND agreement, though. Yeah.
Well, I think ultimately it's a race for power, right? When we look at it in totality, whether it's the race for AI or the race towards computing power or what have you, it's ultimately a race towards becoming like a superpower in the world, and that was sort of one of the main things we talked about in terms of the AI race, right? That the first country, as it were, to reach AGI is going to have a real advantage. And I think you can see the same thing happening with computing power, with quantum computing and whatnot, right? Because that was the big thing that disrupted the industry recently was DeepSeek that we mentioned
Yeah.
in a recent podcast, and that was born out of this idea that the U.S. had restricted chips being sent over to China, and so that they had to be inventive and figure out how can we run, an LLM at a much lower computing power, and that caused this massive disruption, which is interesting in the sense that up until then, people thought they had to build these massive server farms. So what happens when you figure out how to run, an LLM like DeepSeek on a smaller amount of computing power, and now you're able to run that on a server farm. So in other words, you're just exploding the amount of computing power. And then now combine that with the potential that they're talking about for quantum computing and how that's going to accelerate the AI race.
It's
And
scary. Yeah.
I really do believe that, we talked about this when we started this podcast. I guess, we're in a few months, we're coming up on a year. And, we were talking then like, oh, are they going to achieve AGI? And it might be, we might be talking 5 years, 10 years, 20 years. It was really unknown. And now you're seeing these breakthroughs where the combination of quantum computing, for example, and AI, we could see this sort of level of AGI being reached really quickly. Like it really could accelerate to that level, right? And we're seeing
It's
rapid
definitely
advancement,
we're not
right?
25 years away anymore. Right? Definitely not. I mean, the pace we've seen in 1 year is incredible. And here's the other thing too: is we're actually changing the game too, right? So we're building these these AI agents, and then we're putting them into uh, you know humanoids and robotic self-contained systems, and we're allowing them to continue to change and grow. right? We're going way beyond, the control limits and control components that we have in ChatGPT and Claude, where we got everything locked down and nothing gets, we may have a, session learning there that's occurring, but that's it, right? The core is always the same, right? Not so with these agents, not so with these humanoids and these robots that are now, utilizing AI, and then they're kind of self-evolving, right?
Yeah, we want to
And
give them
they're
autonomy,
unchecked.
right?
Yeah, they're unchecked, right? So, the old science fiction, oh, well, how did they ever figure out how to do this? I mean, you think about it, you see, I've seen it before. I've seen a horse open a door, okay? And you say, how'd that horse learn how to do that, right? It figured it out, right? We're talking about, an animal, which even horses are smart, but they can do some incredible things. You can teach them incredible things, but they can also figure stuff out, right? But when you start thinking about, advanced, the cybertronics and humanoids and, androids and so on and so forth, what are they capable of, right? It's and especially if the controls and the limits aren't there, you aren't getting reset.
We're sort of playing with fire in essence, right?
Yeah.
We're giving them this ability to design their own chips, and we're giving them autonomy, and we're giving them this license, and it's almost like, let's see what happens. If you think about, the idea of
It's insanity.
everything we have today was based on the idea that man discovered fire, right?
Yeah.
If man hadn't discovered fire, we'd all still be running around in caves and hunting for animals and this type of thing. So I mean, this is sort of this. It might be the moment that the humanoids or the AI powered entities have discovered fire, and we're sort of we're unleashing it, as it were, right?
Well, yeah. Here's a body that's stronger and faster than us. Here's a brain, and by the way, what we do is we download that brain with everything that humankind knows of, all of its knowledge, and we build that and we download that, right? Now, I know I'm exaggerating a little bit, but put that in perspective, right? And really start thinking about that, right? What are we doing here? Are we building a time bomb? Are we building the atom bomb? No, we're building an autonomous being, right? It's going to figure out shit, right? And it is not going to rely on us, right? And if we're going to build 1,000 of them, we're going to build 1,000,000 of them. How many we're going to build? I don't know.
Yeah, well, I figure at some point in the future they're going to be listening to this podcast. So I'll just say, I for one welcome our robot overlords.
Flesh and bone can never see what the chips are meant to be.
Thank you for listening to the Probability Podcast. Please join us next time for more musings from the generator and the discriminator.